What would happen if 95% of all life on Earth disappeared? How has our planet been able to survive catastrophes so devastating that they have almost wiped out all traces of life on its surface? On 5 occasions in our planet's history, the great evolutionary clock has come to an abrupt halt. Events of unimaginable violence transformed the Earth into a hostile world, where survival itself became an impossible challenge. From boiling oceans to acid rain, from asteroid impacts to cataclysmic volcanic eruptions, our planet still bears the scars of these successive apocalypses. Tragedies that have redrawn the maps of life, wiped out dominant species and allowed new forms of life to emerge. Without these moments of mass destruction, we humans would probably never have appeared. Dear traveler, welcome. Today we're off to explore time and discover the mysteries of the great mass extinctions. But before we set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! Imagine witnessing a scene like this. 3 species out of 4 brutally wiped off the face of the Earth forever. First of all, do you know what a mass extinction is? It means the disappearance of at least 75% of species in a geologically short space of time. This concept, established in the 19th century by the pioneers of paleontology, has continued to be refined by successive discoveries. Analysis of the geological record has thus revealed 5 major cataclysmic events. From the earliest to the most recent, the Ordovician-Silurian extinction, the Devonian crisis, the Permian-Triassic hecatomb, the Triassic-Jurassic extinction, and finally, the famous disappearance of the dinosaurs in the Cretaceous-Paleogene. Beyond these 5 major mass extinctions, recent studies have revealed a regular cycle of smaller extinctions, occurring approximately every 27 million years. Although these extinctions are not as cataclysmic as the major events, they do mark significant disturbances in terrestrial and marine biodiversity. The causes of this periodicity remain unclear. Some scientists suggest that it could be linked to galactic oscillations that expose the Earth to increased radiation, or to disturbances in the Oort cloud, causing an increase in cometary impacts. Other hypotheses include the passage of dying stars, or cycles within the solar system. Although these theories are still debated, they underline the profound influence of cosmic phenomena on the history of life on Earth. Our mission today will probably not be able to lift the veil on this mystery, but analyzing the course of successive extinctions could nonetheless bring us closer to that understanding. The coordinates are now locked on our first destination, the Ordovician-Silurian extinction. Prepare to plunge into a world where the continents were still untouched by terrestrial life, and the oceans teemed with creatures now extinct. Time coordinates locked at 444 million years BC. Our first stop takes us to the heart of the oldest documented mass extinction. Research up to the 21st century has painted a picture of a mainly oceanic cataclysm, upending a world still devoid of complex terrestrial vegetation. Pioneering work, which laid the foundations for our understanding of this first extinction, pointed to a phenomenon of destructive glaciation. However, as subsequent observations have shown, the causes appear to be far more complex, and the hypotheses have followed one another ever since. Could a hypernova in our galactic neighborhood have triggered the gamma-ray explosion? Could intense volcanic activity have expelled sulfur into the atmosphere, cooling the planet's climate and causing persistent anoxia? Or could the impact of a sufficiently massive asteroid have triggered this period of glaciation? Geochemical analyses have since considerably refined this picture, pointing to a cascade of events spanning hundreds of thousands to 1 million years. This period, which represents only a blink of an eye on the geological scale, would have seen the marine world collapse in two distinct phases. The first coincided with an enigmatic intense glaciation that mainly affected shallow water organisms. The second, marked by rapid warming and oceanic anoxia, would have completed the decimation of deep-sea ecosystems. The scale of this extinction is beyond comprehension. Almost 85% of marine species were wiped off the face of the Earth. Among the victims are the trilobites, the undisputed masters of the Ordovician oceans. They saw 60% of their fellow creatures disappear. Graptolites, emblematic floating colonies of the period, came close to total annihilation. Stromatoporoid reefs, massive organic structures that dominated shallow seas, have all but disappeared. Nevertheless, their near disappearance opened the way to new forms of life, redefining Silurian marine ecosystems in the making. The consequences of this extinction have shaped the evolution of marine life for millions of years. But one of the most intriguing discoveries concerns the potential role of tectonic movements in triggering this crisis. Studies dating back to 2022 suggest that a rapid shift of the Earth's magnetic poles, a phenomenon known as the true polar wander, could have contributed greatly to these climatic upheavals. This hypothesis, if confirmed, would add a new dimension to our understanding of large-scale extinction mechanisms. What's more, the Ordovician-Silurian event raises crucial questions about the resilience of ecosystems. How did some species survive this cataclysm, while others, apparently just as adapted, disappeared? The composition of the air is radically different from today. Oxygen concentration is 80% of the level we are used to. Atmospheric carbon dioxide levels, on the other hand, are extremely high, 14 to 16 times higher than today's levels. The atmosphere is laden with volcanic particles, confirming the hypothesis of sustained volcanic activity. The holographic reconstruction reveals an unrecognizable world. During this period, the four main continents, including the supercontinent Gondwana, had no apparent vegetation. The coasts are bordered by vast expanses of ice, attesting to an ongoing glaciation. Let's dive beneath the surface. The oceans reveal a surprising acidity, with an average pH of 7.8, significantly lower than previous estimates. This acidification, probably due to the massive absorption of carbon dioxide, partly explains the heavy disappearance of calcareous-shelled organisms. Analyses show an abrupt drop of 10 degrees Celsius or 50 degrees Fahrenheit in just 10,000 years, followed by an equally rapid rise. These extreme oscillations correspond perfectly to the two extinction phases identified by paleontologists. Analysis of the volcanic rock reveals a composition similar to that of the Siberian traps, albeit in different locations. Along certain continental margins, we can observe vast magmatic provinces. We can see that they release huge quantities of greenhouse gases. Sedimentary cores tell a fascinating story. Anoxic layers multiply in deep marine sediments, indicating massive deoxygenation of the oceans during this critical period. These dead zones are spreading rapidly, smothering marine life over considerable areas. Carbon dioxide measurements are reaching staggering levels, far beyond what we know today. This sudden increase coincides with melting ice and the release of methane trapped in underwater hydrates, creating a major greenhouse effect. At the start of this process, the species census reveals a marine world of unsuspected richness, but on the brink of collapse. Reefs are explosions of life. Stromatoporoids, those strange sponge-like organisms, build complex structures, sheltering a multitude of species. Graptolites float like animated lace. These microscopic marine creatures, as elegant as they are mysterious, evolve in dense colonies while filtering plankton. Trilobites in all their diversity still dominate the seabed. We even see a few specimens of Isotellus, the largest trilobite ever discovered, measuring almost a meter in length. But the spectacle soon becomes macabre. Shallow water organisms are the first to suffer. Trilobites and brachiopods die in mass, the remains of their shells covering the seabed. Graptolites, unable to adapt to the rapid changes in temperature and acidity, are disappearing almost entirely. In the abyss, the situation is not much better. Anoxia is gaining ground, creating vast underwater deserts. Only a few organisms adapted to low oxygen concentrations manage to survive in these extreme conditions. In the midst of this chaos, some species show remarkable resilience. We identify populations of conodonts, those enigmatic primitive vertebrates, which seem to be adapting as best they can to these new conditions. Some species of brachiopods, notably those of the Lingula genus, show astonishing resilience. Lingula brachiopods have managed to persist through not one, but all subsequent extinctions. Often referred to as living fossils due to the apparent morphological stability of their shells over geological ages, these brachiopods still populate our oceans. To better understand this defense mechanism in the face of an increasingly hostile environment, further study is required. Genetic analysis of survivors reveals fascinating adaptations. Some species develop more efficient internal pH regulation mechanisms, while others modify their metabolism to resist anoxia. These evolutionary innovations will lay the foundations for the explosive diversification of the period to come, the Silurian. But the most surprising is yet to come. Colonies of cyanobacteria and primitive algae began to take over coastal areas, foreshadowing the future conquest of continents by plants. This extinction, however devastating, has paved the way for new, more adapted and resilient forms of life. The extreme climate changes we have measured corroborate the hypothesis of devastating thermal oscillations. We observed a period of massive continental glaciation lasting around 500,000 years at the end of the late Ordovician, causing a drop in sea levels. A few 100,000 years later, rapid warming, just as impactful, delivered the second coup de grace. These fluctuations correspond perfectly to the two extinction phases identified by paleontologists, underlining the direct impact of climate on the biosphere. The chain of catastrophic events can be seen with unprecedented clarity. A drop in sea level of at least 50 meters or 165 feet during glaciation is also a key factor in the disruption of marine ecosystems. Africa's position on the South Pole was a key factor in triggering the glaciation, despite high levels of carbon dioxide. The impact on ecosystems is broadly in line with projections based on the fossil record to date. Among the survivors, we have identified new colonial organizations and graptolites, demonstrating the capacity of certain species to adapt to these drastic environmental changes. Ocean circulation also played a crucial role in the extinction. Unlike today, the deep water of the Ordovician period came from warm, salty, tropical, epicontinental seas. The result? Slow ocean circulation and anoxic conditions in deep waters. And this aspect is essential, as it highlights the importance of changes in ocean circulation. Glaciation lowered sea levels, modifying and accelerating ocean circulation. One thing led to another, and these changes led to the upwelling of deep waters rich in toxic substances. The occurrence of these so-called eocenic conditions, limiting the availability of oxygen, could explain the massive mortality of graptolites in particular. This reveals the importance of oceanic gyres in the distribution of nutrients and oxygen. The large gyres of the Panthalosic, these sets of ocean currents, and the smaller ones of the Paleotethys and Lapitous oceans, therefore played a central role in regulating climate and the distribution of marine life. The complex interplay between plate tectonics, ocean circulation, and climate has created a perfect storm for the biosphere. There is no confirmation that an event outside our planet, such as a gamma-ray bombardment or the arrival of a massive meteorite, has taken place. But should one of these events ever be confirmed, it will probably not have played a major role in this first extinction. Its consequences, though devastating, paradoxically paved the way for new life forms and ecological organizations. After our exploration of the icy waters of the Ordovician, our time machine is about to propel us tens of millions of years later into the heart of the Devonian. Nicknamed the Age of Fishes, this period also witnessed a major upheaval. Just as terrestrial life was beginning to blossom, with the appearance of the first forests and the first tetrapods, the oceans were struck by a series of cataclysmic phenomena. This second great mass extinction, less well known, but just as devastating as the previous one, will profoundly reshape both marine and terrestrial ecosystems. Prepare to be immersed in a rapidly changing world, where every observation could be the key to deciphering the complex mechanisms governing both the evolution and extinction of species. Time coordinates set to 358 million years ago. Activation of the immersion bubble in 3, 2, 1. As silent witnesses to an ecological catastrophe of unprecedented proportions, we are thrown back into the troubled Devonian period. We find ourselves faced with a veritable time puzzle, where every clue counts to unravel the complex skein of this second great extinction. Coral reefs, once flourishing, are disintegrating before our very eyes, victims of a lethal cocktail of environmental changes. Nutrient-laden water is slowly suffocating marine life. But beware! Contrary to what we thought, it's not a single blow to biodiversity, but a series of climatic setbacks, spanning 500,000 to 15 million years. Analyses reveal dizzying thermal oscillations, alternating between periods of suffocating heat and brutal cooling. Scientists are divided on the causes. Some point to the lightning expansion of land plants, veritable nutrient factories that have considerably upset biogeochemical cycles. Others insist on the role of massive volcanic eruptions, of which the sediments we observe bear fresh traces. Could changes in the Earth's orbit around the Sun have played a role in this planetary drama? The hypothesis of a drastic reduction in the ozone layer, exposing marine life to lethal UV bombardment, seems to be gaining credibility. This extinction cannot be reduced to a simplistic explanation. It's a complex web of cause and effect that we are trying to untangle. Look out! The first real trees stand before us. Stately Archaeopteris dominate the coastal landscape. Their sturdy trunks rise up to 30 meters or 100 feet high, their fan-shaped leaf-covered branches swaying in the primeval breeze. These woody giants with their deep root systems are literally transforming the surface of the Earth before our very eyes, and with good reason. Shoreline erosion is intensifying like never before. The roots of these plants fragment the rock, releasing nutrients at an unprecedented rate. Rock erosion, already significant due to tectonic activity and rising mountain ranges, has reached its peak with the proliferation of trees. A spectacular increase in phosphorus levels in lake sediments. The cycles we observe are striking. Dry periods with phosphorus peaks alternate with wet phases when levels fall. It's as if the Earth itself were breathing to the rhythm of these new plant giants. But this terrestrial spectacle is only a prelude to the drama unfolding in the oceans. Let's dive into the shallows. The influx of nutrients is phenomenal. Before our very eyes, algae proliferate at dizzying speed, forming thick green mats on the water's surface. Light is no longer able to penetrate this increasingly dense plant layer. Coral reefs once flourishing are suffocating. This cruel lack of light only exacerbates the anoxia. We are direct witnesses to the asphyxiation of these dying reefs. As scientists had predicted, the stromatoporoids and tabulate corals that form the backbone of these ecosystems are disappearing at a rapid rate. These reef-building stromatoporoids, reminiscent of our modern sponges, are fading and dying in whole colonies. In turn, benthic communities are in unparalleled distress. They are the hardest hit. Their populations are collapsing in real time. The massive decline of brachiopods has begun. Almost a third of their families have disappeared. Genera such as Stringocephalus and Unsites, which had been ubiquitous, disappeared from the living record. Trilobites, the marine arthropods that had dominated the ocean floor for millions of years, also suffered a fatal blow. Deprived in turn of dissolved oxygen, they could no longer breathe. Emblematic forms such as Phacops and Scutellum, which proliferated in Devonian seas, are dying out before our helpless eyes. It has been calculated that more than 50% of trilobite genera will disappear during this extinction. Our observations show that many primitive ammonite lineages, such as Clymenida, become completely extinct. Even cephalopods, renowned for their resilience, were hit hard. In the space of a few million years, or the flapping of a few wings on a geological scale, almost 75% of marine species have disappeared before our very eyes. As we descend deeper, our oxygen sensors are turning red. The worst is yet to come. Anoxia is spreading like wildfire. The waters, overloaded with decomposing organic matter, consume all the oxygen still available. We are witnessing the formation of vast, inexorably expanding dead zones. Placoderms, the armored fish that once reigned supreme in the oceans, are decimated. The mighty Dunkleosteus, predator at the top of the food chain, will not survive this crisis. Data confirms that placoderms, which numbered over 300 species in Devonian times, became almost totally extinct. Only a handful survived into the Carboniferous before disappearing for good. In shallow waters, even agnathans, jawless fish that had existed since Ordovician times, succumbed to this extinction. It's the end of an era for primitive vertebrates. Indeed, our records show that the last representatives of the genera Pteraspis and Cephalaspis became extinct during this period, marking the end of agnathans as a dominant group. In total, calculations based on future paleontological data estimate that this extinction eliminated almost 90% of reefs composed of tabulate and rugose corals, and between 70 and 80% of marine species. Returning to the surface, we are struck by the stark contrast. While the oceans are dying, life on land seems to be thriving. We can even observe with fascination the emergence of new forms of existence. Extraordinary! The first tetrapods are making their timid appearance. Look, an acanthostega clumsily pulls itself up onto the bank. This half-fish, half-amphibian creature, about 60 centimeters or 23 inches long, perfectly symbolizes the evolutionary transition underway. Although still dependent on water for survival, its primitive, 8-fingered limbs enable it to move awkwardly on land. However, changes are palpable even on land. Let's analyze a few samples. Atmospheric composition is in upheaval. Carbon dioxide levels are dropping drastically, from 4,000 ppm to less than 1,000 ppm in just a few million years. This spectacular drop in carbon dioxide, a direct consequence of the expansion of primeval forests and the intensification of rock erosion, had major climatic repercussions. The formation of ice caps at the poles marked the start of a period of global cooling. Until then, the climate during the Devonian period had been warm and balanced. As we prepare to leave this tumultuous era behind, our gaze fixed on the horizon, one last phenomenon catches our attention. Storms seem more frequent and more intense than ever before. And with good reason. Changes in temperature and atmospheric pressure are creating unprecedented meteorological disturbances. We are witnessing the formation of tropical cyclones of unprecedented power, sweeping along the coasts. UV radiation levels have rapidly tripled. This sudden increase in ultraviolet radiation, possibly linked to a reduction in the primitive ozone layer, is adding further pressure to already fragile ecosystems. Asteroid impacts and volcanic eruptions may also have exacerbated this ecological crisis. We embark on a third spectacular journey back 252 million years to the present day, to the heart of the Permian-Triassic extinction event. Also known as the Great Death, this was our planet's third mass extinction. But before we jump into the time vortex, let's take stock of what we know, or at least think we know, about this cataclysmic episode. The Permian, the last period of the Paleozoic era, was a time of great biological diversity. But in the space of a few tens of thousands of years, up to 96% of marine species and over 70% of terrestrial species evaporated. Several theories attempt to explain this disaster, which resulted in the annihilation of almost 90% of the living world, all species combined. Scientists have identified several potential contributing forces, including massive volcanic eruptions in Siberia, the so-called Siberian traps. Over hundreds of thousands of years, these eruptions poured out torrents of lava, releasing colossal quantities of greenhouse gases, such as carbon dioxide. This emission would have led to rapid global warming, ecosystem collapse, and once again, widespread marine anoxia. The oceans, thus depleted of oxygen, would have become particularly hostile to life. Another hypothesis is that the massive deposits of frozen methane, known as clathrates, were released from the seabed, further accelerating this greenhouse effect. Add to this hypothetical asteroid or comet impacts that would have exacerbated the crisis, and you have an apocalyptic cocktail. Despite a thorough study of the sediments, debates persist. We are now floating above an unrecognizable Earth. At that time, the continents were not at all distributed as they are today. With the exception of part of Southeast Asia, they were agglomerated together by Hercynian mountain chains. The Earth is thus dominated by an immense supercontinent formed in the Carboniferous period, Pangaea. This vast landscape, stretching from pole to pole, is marked by extreme climatic conditions. The interior is particularly arid, with deserts stretching from thousands of kilometers. Temperatures reach dizzying heights during the day before plummeting at nightfall. This aridity contrasts with the coastal regions, where the influence of the oceans moderates conditions, but not enough to create a clement environment. These harsh climatic conditions pose enormous challenges for biodiversity. Living organisms must adapt to extreme temperatures and persistent drought. Under the scorching sun, vast desert plains stretch as far as the eye can see, dotted with rare oases of greenery. A group of large land reptiles, the periosaurs, move slowly in search of rare vegetation. Their thick skin is studded with scales that protect them from the sun's merciless rays. The arid ground is cracked on all sides, a sure sign of the harshness of the climate. Nearby, a small herd of diconodonts, robust herbivores, feed on the rare plants near an almost dried-up waterhole. Predators such as gorgonopsians prowl discreetly, their sharp eyes watching every move, ready to pounce on vulnerable prey. In the depths of the vast and unique Panthalassa Ocean, life abounds beneath the surface. Vast coral reefs, ancestors of those we know today, are home to a myriad of creatures. Dominated by tabulates and ruffs, they create an ecosystem of unprecedented complexity. Schools of goniatites, Crenistria, drift peacefully by, their spiral shells reflecting the light. Numerous Phacops ranatrilobites glide along the seabed, their complex eyes scanning the surroundings, while a few prehistoric fish, protected by bony plates, swim nimbly among the corals. Schools of fish move in sync, creating hypnotic dances of light and shadow. From time to time, a massive predator, the prehistoric Hybidus shark, cuts through the waters with fearsome power in search of its next prey. If the landscape before us is breathtakingly rich, we know that this abundance is about to collapse. In fact, our instruments are reporting abnormal activity in an area to the north that will become Siberia. The Earth is beginning to roar. The process has begun. The Siberian traps, that gigantic volcanic region, have just erupted. Abundant streams of lava are pouring out. And as we already know, they will do so for hundreds of thousands of years, covering millions of square kilometers. Mountains of fire hurl kilometer-high columns of ash, darkening the skies. Sulfur particles mix with the atmosphere, blocking the sun's rays, and a rapid cooling sets in. It's an era of darkness where the days turn to twilight. But this destructive lava is not the only one to strike. A few decades later, the greenhouse gases released by these volcanoes reverse the phenomenon. These massive eruptions release astronomical quantities of greenhouse gases into the atmosphere, notably carbon dioxide and methane. The deep blue waters of the oceans are becoming increasingly murky and swampy. Planktonic organisms collapse, disrupting the entire food chain. Anoxia begins. Entire areas of the seabed become dead, leaving only bacteria to release toxic gases. Imagine the surrounding stench, a mixture of sulfur and decay, a perfume of death that envelops the planet. Coral reefs, once vibrant underwater forests, are disintegrating before our very eyes, as if reduced to dust by an invisible force. Their disappearance will last for millions of years. As heat increases, desert zones spread across continents, trapping land creatures in ever smaller enclaves. We fly over the continent of Pangaea, where tree fern forests are turning brown and dying, and resources are becoming scarce. The Permian forest, hitherto dominated by these giant ferns and primitive conifers, are rapidly being devastated by this increasingly arid weather and by atmospheric pollution, attributed to incessant eruptions. While the emerald green of the conifers may at first appear to survive in these extreme conditions, life is already struggling against implacable forces. Plants are dying, depriving herbivores of their food. Diconodons, Lacerticips, wander desperately. With the dry land offering them nothing, they are reduced to chewing poisonous plants in a last-ditch attempt to survive. Only a few diconodonts survive to give rise to modern mammals. Large mammalian reptiles such as Gorgonopsians starved and collapsed in their turn, these predators being unable to survive without prey. Huge primitive amphibians, once masters of the marshes, are suffocating in the few remaining water holes where toxins concentrate. With climate change almost wiping out their wetland habitat, they are disappearing one by one. But the situation is even worse in the ocean, which is gradually becoming a veritable aquatic graveyard. Carbon dioxide dissolves in the water, causing massive acidification. The shells of sea creatures begin to dissolve. Aquatic life suffocates as oxygen disappears from the depths, leaving countless dead zones. Trilobites, marine arthropods that have been around for hundreds of millions of years, are disappearing one after the other, like this Phacops rana, whose gills are no longer able to capture the dwindling oxygen. After surviving several crises, they were unable to withstand the extreme conditions of the Permian-Triassic. Goniotites crenistria, victims of lethal hypercapnia, swim erratically before succumbing. Crinoids such as sea lilies and ophiuroids, echinoderms close to sea stars and modern sea urchins, are all but eradicated. Volcanic eruptions also trigger chain reactions. Under the ocean floor, deposits of frozen methane are suddenly released. This super powerful gas amplifies the greenhouse effect, transforming the Earth into a deadly steam room. On the continent, the extreme heat caused devastating fires. The air becomes unbreathable, saturated with ash and toxic gases. Animals collapsed, suffocated, no longer able to fight. In just a few 100,000 years, over 90% of marine species and 70% of terrestrial species have become extinct. In the midst of this chaos, a few rare survivors cling to life. To escape the heat, the Lystrosaurus finds refuge underground. Able to dig a burrow, this herbivorous therapsid escapes extreme temperatures. Feeding on roots and emerging from its burrow at night to find provisions, it avoids the deadly daytime temperatures. A little further on, a small reptile, the Procolophon, also seems to survive. Scrambling between the rocks of this arid land, it feeds on small insects and tough plants. Its small size, low metabolism, and ability to feed on a variety of foods make it a survivor in the making. In the ocean, a brachiopod able to live in shallow waters and tolerate relatively low oxygen levels is once again demonstrating extraordinary resilience. This is Lingula, which can be seen clinging to rocks in colonies, resisting the waves of warm acidic waters. Alongside Lingula, other orders of brachiopods such as Crenida, Rhinoconolida, and Terebratulida also adapt to this inhospitable environment. A family of Nautilidae cephalopods is also proving extremely resilient. Cenoceras, a carnivorous mollusk with the ability to regulate the internal pressure of its shell, can venture into deeper waters. It thus escapes the toxic, overheated surface waters. The hypothesis of volcanic eruptions and methane releases is indeed the key to this extinction. Moreover, it is the result of a long agony, estimated to have lasted between 60,000 and 200,000 years for the main peak. However, the observed disturbances probably extended over 1 million years. The scenario of an asteroid impact, while possible, does not resonate here, especially as no significant craters have been identified during this period. The eruptions of the Siberian traps changed the course of life on Earth forever. After the Great Permian Extinction, the Triassic period, which stretches from around 252 to 201 million years BC, marks an era of rebirth. It was a time of transformation, when new groups such as the first dinosaurs and mammals began to emerge in ecosystems that were still unstable and dominated by Archosaurian reptiles. Unfortunately, this period also ended in one of the most devastating and enigmatic exterminations in Earth's history. Before embarking on this extraordinary journey, let's take stock in what we know about the Triassic-Jurassic extinction. According to scientific studies, this major biological crisis caused the annihilation of around 76% of marine and terrestrial species. Unlike the more massive Permian-Triassic extinction, or the much more publicized Cretaceous-Paleogene extinction, the Triassic-Jurassic crisis remains relatively unknown to the general public. Several hypotheses have been put forward to explain this cataclysmic event. The least supported theory is that of an asteroid impact. A collision with a massive celestial body could have triggered rapid environmental changes. Another postulate suggests that major fluctuations in sea levels could have disrupted coastal and marine ecosystems. Others point to changes in ocean circulation. A disruption in ocean currents could therefore have affected the distribution of nutrients and oxygen in the seas. The idea of a warming of the oceans causing the sudden release of large quantities of methane, amplifying the greenhouse effect, has also been put forward. Some have also suggested that this gradual extinction could be due solely to strong competition between different species. But the most plausible hypothesis to date remains that of intense volcanic activity. Massive eruptions would have triggered an irreversible process, the consequences of which we now know. How about solving this 201 million year old mystery? Comfortably seated in our time capsule, heart pounding, the countdown begins. As the landscape around you dissolves into a swirl of colors, you recognize that feeling where every atom in your body seems to disintegrate before calm returns. When you open your eyes, you find yourself in a totally unfamiliar world. The air is heavy, laden with the acrid smell of sulfur. The sky is an ominous orange-red with lightning flashing across it. You realize you're in the midst of another major biological crisis since the Permian-Triassic extinction. Atmospheric analysis reveals carbon dioxide levels as high as 2,000 ppm, more than 5 times those of modern times. Now let's take a look at the aquatic environment. The average pH is 7.6, while that of seawater is usually 8.1. Such acidity partly explains the massive disappearance of calcareous-shelled organisms, whose countless corpses cover deserted beaches. Gigantic fissures in the Earth's crust spew streams of lava, releasing clouds of ash and toxic gases. We preview the formation of the Mid-Atlantic Magmatic Province, one of the largest incandescent regions in Earth's history. the flow of lava is unimaginable. According to our instruments, over 3 million cubic kilometers of magma will be ejected over a period of 600,000 years. This massive volcanic activity releases huge quantities of carbon dioxide and sulfur compounds into the atmosphere, explaining the extreme climatic conditions you're observing. Taking rock samples from different depths provides further information. Analysis reveals successive layers of volcanic ash, confirming the pulsatile nature of the Central Atlantic magmatic province's eruptions. Between these layers, we can identify sediments rich in iridium, a rare element on Earth but common in meteorites. De facto, this discovery revives the hypothesis of an extraterrestrial impact as an aggravating factor in the current extinction. For the living world, these extreme conditions are hardly advantageous. The species census reveals a macrocosm in upheaval. In the oceans, we are witnessing the mass disappearance of ammonites, the spiral-shelled mollusks that dominated the Triassic seas. Only a few species, such as Siloceras, Planorbis, seem able to survive, probably thanks to their small size and ability to withstand poorly oxygenated waters. We're looking at a veritable conodont graveyard. These primitive eel-like vertebrates, which thrive for hundreds of millions of years, cover this area by the millions. It was their mass extinction that marked the end of the Triassic and the beginning of the Jurassic. Many brachiopods also suffered mass extinctions. Spiriferanida, such as Spiriferanira walcoti, disappeared completely. Worse still, larger creatures have not been spared. Among the placodonts, Placodus gigas, a battleship marine reptile, was wiped out. The same goes for Nothosaurus mirabilis, the reptilian ancestor of the plesiosaurs, which has no choice but to bow out. Many lineages of fish have also been greatly affected. Among the monsters of the deep was Shawnosaurus, whose specimens measured up to 21 meters or 70 feet in length. The ichthyosaur group was not spared. Nevertheless, in the midst of this desolate picture, there are a few signs of hope. Some species have shown remarkable resilience. While many groups of bivalves have been hard hit, such as Megalodontidae and Megalodon triqueter, which have become extinct, others are resisting. Bivalves of the genus Modiolus, for example, seem to thrive in these acidic, low-oxygen waters. Their ability to hermetically seal their shells for long periods is undoubtedly their trump card. In this way, they can survive these extreme conditions. On land, the landscape is just as desolate. The forests of Dicroidium, the seed ferns that once covered vast areas, have almost entirely disappeared. In their place are the first shoots of conifers, more resistant to the new climatic conditions. Many terrestrial species succumb to this hostile environment. Rutiodon carolinensis, a 3-meter or 10-foot long semi-aquatic reptile belonging to the phytosaur family, will never again dominate its freshwater ecosystem. Desmatosuchus spirensis, a battleship herbivore 5 meters or 15 feet long, is also disappearing. All groups are heavily impacted. The losses are colossal. From primordial pterosaurs to herbivorous cynodonts and primitive amphibians, all saw their lineage reduced to almost nothing. However, small theropods, the ancestors of the dinosaurs, seem to have adapted remarkably well to this new environment. Their high metabolism and small size enable them to survive with limited resources. Small primitive mammals, such as Morganeucodon and Cynoconodon, 'Cynoconodon, also seem to have been able to withstand these extreme conditions. The Their varied diet and modest size enable them to adapt more easily to these rapid environmental changes. In fact, although this may seem like a catastrophic observation, you probably realize that you're witnessing a fantastic moment. It's the dawn of the mammalian era, the creatures that will one day flourish on our beautiful planet. Genetic analysis of the survivors reveals some fascinating adaptations. Some fish species have developed more efficient blood pH regulation mechanisms, enabling them to withstand ocean acidification. Other organisms show changes in their metabolic pathways, enabling them to survive on less oxygen. Ecological changes have been far too rapid to be due solely to interactions between species. Competition alone cannot therefore be considered. On the other hand, volcanic activity in the mid-Atlantic magmatic province appears to have been the main trigger for this mass extinction. When the Atlantic opened up, emissions of carbon dioxide and sulfur compounds caused global warming and cooling, ocean acidification, and disruption of geochemical cycles on a planetary scale. An analysis of the consequences reveals the scale of the catastrophe. Over 76% of marine and terrestrial species have disappeared in the space of a few 100,000 years, a snap of the fingers on a geological scale. This extinction completely reconfigured ecosystems, paving the way for new forms of life to dominate the Jurassic. Before delving into one of the most emblematic periods in Earth's history, the Cretaceous-Paleogene transition, it's time to review what we know today. The Cretaceous-Paleogene extinction, which occurred around 66 million years ago, marked the end of the era of non-avian dinosaurs and the beginning of the age of mammals. This mass extinction wiped out around 75% of the planet's plant and animal species, drastically reconfiguring terrestrial and marine ecosystems. There are many hypotheses as to the cause of this extinction, which are still being debated in the scientific sphere. The dominant theory, proposed by Luis and Walter Alvarez in 1980, suggests the impact of an asteroid at least 10 kilometers or 6 miles in diameter. The Chicxulub crater, discovered in Mexico, seems to corroborate this hypothesis. However, other theories have also been put forward. Intensive volcanism in the Deccan Traps in India, which would have released huge quantities of greenhouse gases, gradual climate change due to plate tectonics, a series of impacts by comets or smaller asteroids, a nearby supernova explosion irradiating the Earth, changes in oceanic and atmospheric circulation, or even a combination of several of these factors? Despite decades of research, many questions remain unanswered. We're in the Cretaceous period. The temperature is 32 degrees Celsius or 90 degrees Fahrenheit, and humidity is 85%. Carbon dioxide concentration is 1,500 ppm, almost 4 times today's level. Oxygen is 30%, compared with 20% today. The air is heavy with the smell of sulfur and decaying vegetation. You realize you're in a lush jungle, far different from any you've seen in your own time. We've arrived some 2,000 years before the alleged impact. This is the ideal time to establish a database on the pre-extinction ecosystem. Pangaea has long since fragmented, but the continents are still in motion. India, still isolated, is drifting rapidly northwards. This configuration has a profound influence on oceanic and atmospheric currents. Iridium concentrations are already slightly higher than normal, suggesting intense volcanic activity or multiple minor meteorite impacts preceding the main event. In the air, pterosaurs of the species Quetzalcoatlus, Northropi, with their 10-meter or 33 feet wingspan, soar majestically. On the ground, a herd of Triceratops horridus graze peacefully, their enormous bony ruffs gleaming in the sunlight. You spot a furtive moment in the thicket. The biological scanner identifies a small mammal, Purgatorius, one of the presumed ancestors of primates. Its small size and varied diet will enable it to survive the impending extinction. Cretaceous oceans materialize around us. Mosasaurs, like the fearsome Tylosaurus proriger, 15 meters or 50 feet long, hunt in the shallows. Schools of ammonites, including the imposing Parapuzosia sepunredensis, reaching 2 meters or 7 feet in diameter, swim gracefully. The seabed is a spectacle of color and life. Extensive reefs are formed by rudists, bivalve mollusks that are now extinct. Their imminent extinction will leave vacant an ecological niche that modern corals will later occupy. The ground trembles slightly beneath our feet. Intense volcanic activity thousands of kilometers away. This is it! The Deccan Traps in India are erupting. Millions of tons of gas and ash are spewed into the atmosphere, gradually and irrevocably altering the global climate. The atmospheric analyzer detects worrying fluctuations. Carbon dioxide concentrations are slowly but surely rising, leading to global warming. However, volcanic ash suspended in the atmosphere creates a parasol effect, partially offsetting this greenhouse effect. Let's take a leap 2,000 years into the future to witness the dreaded impact. The sky bursts into flames. A luminous object brighter than 1,000 suns passes through the atmosphere at dizzying speed. The impact is so violent that you feel the tremor through the quantum bubble, which is supposed to insulate us from the physical effects of this epoch. The impact generated an earthquake with an estimated magnitude of 11 on the Richter scale, releasing 1 billion times more energy than the famous Hiroshima bomb. A gigantic tsunami, several hundred meters high, swept the coastline. Billions of tons of debris were hurled into the stratosphere, blocking out sunlight. Temperatures plummeted by 20 degrees Celsius, or 68 degrees Fahrenheit, in just a few days. Darkness is almost total. Alarming concentrations of sulfur dioxide and nitrogen oxide float in the air. These gases, combined with atmospheric water vapor, form devastating acid rain. In just a few weeks, most of the great dinosaurs had disappeared. Herbivorous species deprived of vegetation were the first to succumb, closely followed by carnivores. In the oceans, the collapse of the food chain was just as brutal. Large marine predators such as mosasaurs and plesiosaurs rapidly disappeared. Ammonites, which had dominated the seas for millions of years, became almost entirely extinct. Despite this cataclysm, some species managed to survive. Crocodilians, such as Borealosuchus, have a crucial ability to remain dormant for long periods. Certain species of turtle can survive without food for months on end. Small insectivorous mammals, the size of shrews or mice, which feed on insects proliferating on decomposing matter. A few species of feathered dinosaurs, ancestors of modern birds, whose small size and adaptable metabolism enabled them to subsist. Let's take another leap, 10,000 years after impact. The landscape is unrecognizable. The lush Cretaceous jungle has given way to a dusty, windswept desert. Only a few ferns and mosses managed to grow in the impoverished soil. The atmosphere is slowly beginning to stabilize. Carbon dioxide concentration has soared to 2,000 ppm, but the average temperature remains low due to the parasol effect of the dust still in suspension. The geological scan reveals a layer of iridium-rich clay stretching across the entire surface of the globe. This KPG boundary, or Cretaceous-Paleogene boundary, will become irrefutable proof of the impact for future geologists. The extinction was not instantaneous. It took place over a period of several thousand to 100,000 years, with cascading effects on ecosystems before reaching its final peak with an asteroid impact in Mexico's Yucatan Peninsula. The hypothesis of this impact is therefore validated, but its effect was amplified by the pre-existing volcanism of the Deccan Traps. As for species survival, there was nothing random about it. Characteristics such as small size, an omnivorous or insectivorous diet, even the ability to feed on detritus or dead organic matter, as well as a short reproductive cycle and a high rate of generation renewal, are all traits that enable these species to adapt more easily to the difficult conditions created by the asteroid impact. The long-term consequences of this extinction are far-reaching. The disappearance of large reptiles paved the way for the adaptive radiation of mammals. The extinction of ammonites enabled the internal shelled cephalopods, ancestors of octopus and squid, to flourish. The destruction of forests favored the evolution of flowering plants, which are more resilient and adaptable. In the history of the Earth, mass extinctions play a central role in the evolution of life. Among them, we have seen the 5 major events that stand out for their scale and dramatic consequences: the Ordovician-Silurian extinction, the late Devonian crisis, the Permian-Triassic event, the most devastating, the Triassic-Jurassic transition, and the Cretaceous-Paleogene extinction, which saw the end of non-avian dinosaurs 66 million years ago. But beyond these 5 major crises, the history of our planet is littered with minor extinctions, often linked to climatic upheavals, regional volcanic eruptions, or localized astronomical events. Although less cataclysmic, these extinctions have also played a crucial role in the evolution of life, promoting adaptive diversification and modifying ecological balances. In all, several dozen extinction events punctuated the 4.5 billion years of Earth's history. To conclude this journey, 2 particular biological crises, although classified as minor in comparison with the great mass extinctions, deserve special attention. These events, which occurred after the end of the Cretaceous, marked important turning points in the reorganization of ecosystems. The Eocene-Oligocene event around 34 million years ago, and the extinction at the end of the Miocene around 7 million years ago. Around 34 million years ago, our planet underwent a major environmental upheaval, the Eocene-Oligocene event. This period marks a clear boundary between 2 geological eras, associated with drastic climatic changes and an extinction event that reshaped the fauna and flora of both land and sea. Prior to this event, the global climate was remarkably warm and stable, a veritable paradise for thriving biodiversity. During the Eocene, global average temperatures were estimated at around 25 degrees Celsius, or 77 degrees Fahrenheit, with minimal climatic differences between equatorial and polar regions, an exceptional phenomenon compared to later epochs. Concentrations of carbon dioxide in the atmosphere reached around 1,000 ppm, almost 3 times today's levels. This CO2-rich atmosphere fueled a natural greenhouse effect, maintaining mild temperatures even at high latitudes. The Earth was dominated by lush tropical forests that stretched all the way to the polar regions. These ecosystems, composed mainly of broadleaf angiosperms and archaic conifers, were home to a wide variety of plants adapted to warm, humid climates. Palms, magnolias, ficus, and tree ferns dominated the landscape, creating thick canopies that trapped moisture and provided an ideal habitat for many animal species. The terrestrial fauna was equally impressive. Among the predators, creodonts, a group of carnivorous mammals now extinct, dominated. These animals, often compared to hyenas or primitive lions, were endowed with powerful teeth and robust musculature, enabling them to hunt large prey efficiently. Herbivores included brontotherids, gigantic rhinoceros-like horned animals that roamed the forests and plains in search of tender vegetation. Tropical forests were also teeming with archaic primates, distant ancestors of modern apes, who exploited the wealth of trees to feed on fruit, leaves, and insects. Birds of impressive dimensions evolved, such as the gastornis, flightless land birds of imposing stature and powerful beaks. These animals, which could reach heights of over 2 meters, were probably omnivorous. Other, smaller birds, equally well adapted to tropical environments, populated the forests, playing a crucial role in pollination and seed dispersal. Continental positions also differed from those we know today. North America and Europe were still partially connected, allowing exchange between these continents. South America and Antarctica were still connected, slowing polar ocean currents and helping to maintain mild temperatures in the south. Africa was moving away from South America, while India continued its slow collision with Asia, gradually forming the Himalayas. In the oceans, phytoplankton thrived thanks to the stable thermal stratification of the waters. This stratification maintained complex marine ecosystems, supporting populations of mollusks, primitive bony fish, and marine mammals such as basilosaurs. The latter, ancestors of modern cetaceans, could grow up to 18 meters long and occupied the top of marine food chains. Coral reefs, though different from today's, played a central role in marine biodiversity, providing a habitat for many species. The Eocene-Oligocene climate shift is the result of a combination of astronomical, tectonic, and atmospheric factors. The main driving force seems to have been the gradual separation of South America and Antarctica, leading to the formation of the Antarctic Circumpolar Current. This current isolated Antarctica from warm equatorial waters, encouraging the formation of ice caps. At the same time, a significant drop in atmospheric CO2 concentrations from around 1,000 ppm to around 500 ppm in just a few million years accelerated cooling. The Earth's orbital oscillations, known as Milankovitch cycles, also help to regulate glaciation episodes. These cycles, combined with increased erosion of silicate rocks removing CO2 from the atmosphere, caused a sharp drop in global temperatures of around 5 degrees Celsius or 9 degrees Fahrenheit over a relatively short period. This cooling had far-reaching consequences for biodiversity. Tropical ecosystems were the first to suffer, with a massive contraction of rainforests. The once verdant polar regions were rapidly invaded by tundra and glacial zones. The loss of these habitats led to the extinction of 20 to 25% of terrestrial mammal species, with an almost total disappearance of archaic primates in North America and Europe. Large herbivores such as brontotherids disappeared completely. Marine mammals also suffered significant losses, notably protocetaceans, ancestors of modern whales. In the oceans, thermal stratification was disrupted, leading to a temporary collapse of phytoplankton populations and marine food webs. Despite this crisis, some lineages managed to adapt. Smaller mammals able to survive on limited resources thrived in cooler, more seasonal environments. Rodents and insectivores, for example, rapidly diversified their ecological niches. In the ocean, some species of pelagic fish and mollusks evolved to adapt to new oceanic conditions. Cold water corals began to colonize the seabed in the emerging polar regions, marking a complete reorganization of marine ecosystems. The cooling of the Oligocene marked the beginning of an era dominated by open habitats such as savannas and steppes. These ecosystems favored the evolution of new types of mammals, notably proboscideans, ancestors of elephants, and modern ruminants. The evolution of grasses played a crucial role, as they became the food base for terrestrial herbivores. On the oceanic front, the formation of the Antarctic ice caps gradually stabilized the world's climate, although the cyclical variations of the ice ages continue to influence global ecosystems. Increased oxygen levels in deep waters, favored by cooling, led to the expansion of certain benthic species. Let's end our journey by heading back some 7 million years to the end of the Miocene, which was marked by a climatic and ecological event of considerable magnitude. This period, which preceded the emergence of the Holocene, was characterized by spectacular changes in the composition of terrestrial and marine ecosystems. Before this extinction, the Earth was a world in transition. The Middle Miocene had been a time of lush forests and warm climates, but the millions of years preceding the final crisis had already seen progressive cooling and increased drought. The continents were close to their current positions. The collision between Africa and Eurasia had closed the Tethys Ocean, making way for the Mediterranean Sea. In Asia, the Himalayan foothills, forming as a result of India's collision with Eurasia, had altered climatic patterns, contributing to the creation of the Great Savannas. The polar ice caps, although still limited, had expanded, causing sea levels to drop by around 70 meters or 230 feet from their current levels. The terrestrial fauna of the late Miocene showed exceptional biodiversity, marked by adaptive evolution to the open habitats that had replaced tropical forests. Among the mammals, proboscideans occupied a central position. Gomphotheriums, imposing mastodons with elongated and often curved tusks, roamed the plains in large herds. They cohabited with the first modern elephants, more compact and better adapted to varied environments. These gigantic herbivores played a crucial role in seed dispersal and landscape modification. At that time, ruminants were in the throes of diversification. Giraffes, the ancestors of today's giraffes, already had elongated necks, although they were less extreme than their modern descendants. Primitive cattle, such as Protragoceras, also roamed these savannas, grazing on the C4 grasses that gradually dominated the vegetation. These plants, particularly efficient in dry, carbon dioxide-poor climates, had established themselves in regions where the subtropical forests had retreated. At the top of the terrestrial food chain were the Machaerodontines, commonly known as saber-toothed tigers. These predators, with hypertrophied canines reaching up to 28 centimeters, were specialized in hunting large prey. Amphicyonids, nicknamed bear dogs, were large opportunistic carnivores. Although by this time their decline had begun, they remain present in forest and open ecosystems, exploiting a wide range of ecological niches. Subtropical forests, which once dominated vast swaths of the northern hemisphere, were rapidly retreating. They were replaced by savannas and steppes, ecosystems better adapted to irregular rainfall and often poor soils. Vegetation was dominated by C4 grasses, which had an adaptive advantage thanks to their ability to capture carbon in arid conditions. This radical change in flora impacted herbivore diets, favoring those capable of digesting the hard fibers of grasses. Africa was in the process of being connected to Eurasia by the closing of the Tethys Sea, giving rise to continuous terrestrial ecosystems. This transition facilitated faunal migrations between the two continents, allowing the exchange of species such as proboscideans and certain carnivores. In South America, carnivorous marsupials still played the role of super predators, although their habitats were increasingly limited by the emergence of arid conditions. In the oceans, marine food webs remain complex, but were beginning to feel the effects of climate change. Baleen cetaceans, or Mystocetes, were expanding rapidly, exploiting abundant populations of krill and small pelagic fish. Odontocetes, like primitive dolphins, occupied a variety of hunting niches. Gigantic sharks, notably the megalodon, still dominated the seas as apex predators. With an estimated length of 18 meters or 60 feet and a bite capable of devouring up to 18 tons of pressure, they preyed on cetaceans and other large prey. The late Miocene event seems to have been triggered by a combination of climate change and geological upheaval. Global cooling accelerated, with an average drop in global temperatures of up to 4 degrees Celsius or 8 degrees Fahrenheit within a few 100,000 years. The Antarctic ice caps expanded, causing sea levels to fall and coastal habitats to fragment. The transition to drier climates was amplified by the progressive closure of the Strait of Gibraltar. This temporarily transformed the Mediterranean Sea into a hypersaline basin during the Messinian salinity crisis. This event, coupled with a drop in atmospheric CO2 levels below 300 ppm, reduced photosynthesis and primary productivity, affecting both terrestrial and marine food chains. Massive volcanic eruptions, notably in East Africa, contributed to a temporary release of particles and gases into the atmosphere, further cooling the climate. The Earth's orbital oscillations, which modulate the distribution of solar energy, also played a role in these drastic changes. The end of the Miocene saw the disappearance of some 15 to 20% of terrestrial and marine species. Among mammals, many extinct lineages were highly specialized, unable to adapt to more arid environments. Amphicyonids disappeared completely, as did several species of large herbivores, such as Gomphotheria in Eurasia and North America. Among reptiles, giant tortoises were greatly reduced in diversity. In the oceans, megalodon populations declined rapidly, probably due to a reduction in available prey. Benthic organisms also suffered from thickening ice sheets, which altered the flow of nutrients to the seabed. Tropical corals were largely destroyed by reduced surface temperatures. After this extinction, the world's ecosystems underwent a major reorganization. Savannas and steppes, which had begun to expand before the crisis, became the dominant habitats over vast areas of Africa, Asia, and South America. This favored the evolution of gregarious mammals, such as horses and antelopes, better adapted to these environments. Each extinction event, whether vast or localized, shapes the contours of evolution on Earth, marking profound inflections in the history of life. Far from being mere interruptions, these cataclysms act as tipping points, forging new balances and giving rise to unexpected forms of life. Crossing the ages and overcoming every crisis, biodiversity bears the marks of a remarkable resilience, a breath of fresh air that transforms every extinction into an opportunity for a different future. And so, over millions of years, the great story of evolution is woven together, linking the great upheavals of the past to the profound history of our living world. Seen from the sky in a million years' time, the Earth won't change that much. Sure, the continents will move, but no more than 45 to 60 kilometers or 30 miles from their current locations. The sun will continue to shine, rising every 24 hours, and the moon will orbit the Earth in about a month. But some things will change quite fundamentally. In many parts of the world, irreversible geological processes are transforming the landscape. The vulnerable contours of ocean coasts will change particularly markedly. An active submarine volcano off the southeast coast of the largest of the Hawaiian Islands has already risen above 3,000 meters or 10,000 feet from the ocean floor and is growing every year. In a million years, a new island will rise from the ocean waves, already named Lohi. At the same time, the extinct volcanic islands to the northwest, including Maui, Oahu, and Kauai, will shrink under the influence of wind and ocean waves respectively. With regard to waves, those studying rocks for future changes conclude that the most active factor in changing the Earth's geography will be the advance and retreat of the ocean. A change in the rate of rift volcanism will take a very, very long time to affect this geography, depending on the amount of lava more or less solidified on the ocean floor. Sea level can fall significantly during lulls in volcanic activity, when the rocks at the bottom cool and settle. Scientists believe this is what caused the sharp drop in sea level just before the Mesozoic extinction. The presence or absence of large inland seas such as the Mediterranean, as well as the reunion and breakup of continents, led to major changes in the size of coastal shelf areas. To imagine the world a few 100 million years from now, we need to look to the past for clues to understanding the future. Global tectonic processes will continue to play an important role in changing the face of the planet. Today, continents are separated from one another. Vast oceans separate America, Eurasia, Africa, Australia, and Antarctica. But these immense expanses of land are in constant motion, and their speed is around 2 to 5 centimeters or 2 inches per year, i.e., around 1,500 kilometers or 930 miles in 60 million years. We can establish fairly precise vectors of this movement for each continent by studying the age of the basalts on the ocean floor. Basalt near mid-ocean ridges is quite young, no more than a few million years old. By contrast, the age of basalt near continental margins and subduction zones can reach over 200 million years. It's easy to take into account all these age data on the composition of the ocean floor to rewind the tape of global tectonics over time and to get an idea of the geographical mobility of the terrestrial continents over the last 200 million years. Based on this information, it is also possible to project the movement of continental plates 100 million years in advance. Given the current trajectories of this movement across the planet, it appears that all continents are heading for the next collision. In 250 million years, most of the Earth's landmass will once again become a giant supercontinent. Nevertheless, the exact structure of the future supercontinent remains the subject of scientific controversy. It is possible to take into account the current movements of the continents and predict their trajectory over the next 10 to 20 million years. The Atlantic Ocean will expand by several hundred kilometers or miles, while the Pacific Ocean will shrink by around the same distance. Australia will move north towards South Asia, and Antarctica will move slightly away from the South Pole towards South Asia. Africa will move slowly northwards across the Mediterranean Sea. In a few tens of millions of years, Africa will collide with southern Europe, closing the Mediterranean Sea and erecting a Himalayan-sized mountain range at the site of the collision. So the map of the world in 20 million years' time will look a little familiar. When modeling a map of the world 100 million years from now, most researchers identify common geographic features. For example, agreeing that the Atlantic Ocean will exceed the size of the Pacific Ocean and become the largest water basin on Earth. According to the extraversion theory, the Atlantic Ocean will continue to open up, and the Americas will eventually collide with Asia, Australia, and Antarctica. In the final stages of this supercontinent assembly, North America will close the Pacific Ocean to the east and collide with Japan, and South America will wind clockwise from the southeast, joining the equatorial part of Antarctica. All these parts are astonishingly combined with each other. Thus, the new supercontinent will be a single continent, stretching from east to west along the equator. The extraversion model mainly maintains that the large convection cells in the mantle, located beneath the tectonic plates, will remain unchanged in their current form. In contrast, the alternative approach, known as introversion, takes the opposite stance, referring to past cycles of closure and opening of the Atlantic Ocean. Today, both supercontinent theories, extraversion and introversion, remain popular. Whatever the outcome of this discussion, everyone agrees that while in 250 million years, the Earth's geography will change significantly, it will still reflect the past. According to some simulations, in around 200 million years' time, average temperatures on Earth should fall slightly, below 12 degrees Celsius or 53 degrees Fahrenheit. At the same time, global sea levels will fall by around 200 meters or 650 feet. In this configuration, conditions for the development of complex life will remain quite favorable at low and mid-latitudes. Only after around 400 million years will average surface temperatures fall to around 10 degrees Celsius or 50 degrees Fahrenheit, and ocean levels drop by more than 500 meters or 1,640 feet from their current position. In this situation, all continents from north to south, even at moderate latitudes, will be covered by glaciers, and mountainous regions at equatorial latitudes will also be frozen. However, this cold snap will not be permanent. After a further 200 to 300 million years or so, an equilibrium should be established between the decrease in temperature due to the bacterial elimination of nitrogen from the atmosphere and the increase in the sun's luminosity. the temporary assembly of continents around the equator will mitigate the impact of ice ages and moderate changes in sea level. Where continents collide, mountain ranges will rise, climate and vegetation will change, and oxygen and carbon dioxide levels in the atmosphere will fluctuate. These changes will be repeated throughout Earth's history. A gamma-ray burst, or huge supernova, occurs less than 6,500 light-years from Earth, within 500 to 600 million years. Gamma-ray bursts are enigmatic phenomena that appear to be the most intense and energetic explosions in the universe, and astronomers assume that they are linked to extremely powerful supernovae. Fortunately, we have yet to observe a gamma-ray burst close enough to us to fully understand what is happening. So far, gamma-ray bursts have only been detected in other galaxies. But if such an event were to occur close to home on a cosmological scale, as it will in around 500 million years' time, less than 6,500 light-years from Earth, it could lead to a mass extinction. A gamma-ray burst directed in our direction, lasting just 10 seconds, could destroy at least half of the Earth's ozone layer. Large-scale ozone depletion could have devastating consequences on food chains, leading to the death of many species. A gamma-ray burst would annihilate life forms on the Earth's surface and in the upper layers of the ocean, which currently supply significant quantities of oxygen to our atmosphere. It turns out that gamma rays also decompose the oxygen and nitrogen present in the atmosphere. These gases would be transformed into nitrogen dioxide, better known as smog. This would envelop the sun over heavily polluted areas. If this smog were to cover the entire Earth, it would block out sunlight and trigger a global ice age. Due to tidal forces, the Moon has moved more than 20,000 kilometers or 12,000 miles away from the Earth. Even in the most favorable cases, the lunar disk can no longer completely cover that of the Sun. In 600 million years' time, all eclipses will be annular. The fate of the Earth is intimately linked to that of the Sun, which, like other stars, cannot shine forever. 50 million years after the Sun's formation, our star became a main sequence star. Since then, its luminosity has increased in an almost linear fashion, rising by around 1% every 110 million years. Within 600 million years, our Sun will undergo a gradual transformation, resulting in a progressive increase in both brightness and heat. This increase in the Sun's luminosity will have a significant impact on our planet, resulting in more solar radiation reaching the Earth. This increase will have an impact on the silicate minerals present on the planet, leading to increased weathering of these minerals. This, in turn, will affect the carbonate-silicate cycle, which is a geochemical process involving the interaction between carbonate and silicate. Increased weathering of surface rocks traps carbon dioxide in the soil in the form of carbonate. As water evaporates from the Earth's surface, rocks harden, leading to a slowdown in plate tectonics, which eventually comes to a halt when the oceans completely evaporate. With less volcanism to recycle carbon into the Earth's atmosphere, carbon dioxide levels begin to fall. For hundreds of millions of years now, the Earth has been experiencing a period of intense cold, with an average surface temperature of around 10 degrees Celsius or 50 degrees Fahrenheit. But now, the sun's increasing brightness is triggering a rise in the Earth's temperature, generating a series of problems. The first signs of trouble will appear within 600 million years, but it's only when the average temperature reaches 47 degrees Celsius or 117 degrees Fahrenheit, when solar luminosity is 10% higher than at present in 1.1 billion years' time, that the situation will become critical. From that point onwards, the Earth will begin to lose water progressively, resulting in a modification of its atmosphere and becoming a humid greenhouse due to the massive evaporation of surface water. At this point, the amount of water in the stratosphere should increase. These water molecules will be broken down by the sun's ultraviolet radiation via the process of photodissociation. As a result, hydrogen will escape from the atmosphere. The main result should be the disappearance of the oceans in around 1.1 billion years. This water vapor, raised in the stratosphere, will undergo chemical decomposition, separating into oxygen and hydrogen. This is when major changes will take place. Higher temperatures will cause the oceans to absorb more carbon dioxide, a gas essential to plant life. This absorption will reduce the amount of carbon dioxide in the atmosphere, causing an imbalance in the plant life cycle. It is estimated that the planet will be able to support highly organized life for another 600 million years from now, as current forecasts indicate that after this period, the sun's increasing brightness will have a significant impact on the biosphere. The emerging scenario is therefore worrying, as not only will the Earth progressively lose its precious water, but also gas is vital for plant development. Together, these elements threaten the delicate balance of our ecosystem. The high temperatures projected for the future would cause the oceans to absorb more carbon dioxide, which would disrupt the biological processes essential to plant life, accelerating the problems associated with water loss and the degradation of our atmosphere. We will be approaching the Earth's carbon dioxide compensation limit, a critical point at which the balance between carbon dioxide and oxygen becomes unsustainable for photosynthesis. In around 600 million years' time, carbon dioxide levels will be lower than those needed to maintain the C3 carbon fixation by photosynthesis used by trees. Some plants, using C4 carbon fixation, can survive carbon dioxide concentrations as low as 10 ppm. Currently, 99% of plants use C3 photosynthesis. Their ability to convert sunlight into energy is gradually declining, leading to a general decline in plant biomass. If atmospheric CO2 levels fall, the survival of embryophytic plants becomes difficult, as they require a minimum concentration of around 10 ppm atmospheric CO2. It is highly probable that the evolution of living organisms will enable a certain number of organisms to adapt to these conditions by using a more efficient photosynthetic carbon acquisition mechanism. When levels fall below this value, complex plants begin to die, leading to a reduction in oxygen production. This decrease, combined with continued consumption by biota and oxidation of kerogen, which is organic carbon in sedimentary rocks, leads to a gradual decline in the atmospheric oxygen until it reaches zero within a few million years. Researchers estimate that plants that use the C3 photosynthesis process to fix atmospheric carbon dioxide should disappear in 600 million years, and C4 plants in 840 million years at the latest, due to the loss of carbon dioxide from the atmosphere. This massive disappearance of plants would have devastating consequences for all living beings as we know them today. Plants are at the very base of the food chain, providing food and energy for herbivores. Their decline means fewer food resources for herbivores, which in turn suffer adverse consequences. Their populations begin to decline, upsetting the balance of ecosystems. Without plants to produce oxygen through photosynthesis, animals would face a disastrous situation. Large endothermic animals, such as mammals and birds, would probably be the first to disappear, due to their higher oxygen requirements, compared to smaller endothermic and ectothermic animals. As atmospheric oxygen levels fall and temperatures rise, placental mammals will become particularly vulnerable. Not only do they have higher oxygen requirements than non-placental mammals, but embryonic development is also highly sensitive to excessive heat. Large herbivorous mammals would suffer from diminishing food resources as plant availability declines. Small mammals would be slightly less affected due to their lower oxygen requirements and surface-to-volume ratio, which facilitates heat dissipation. Placental mammals experience higher body temperatures than marsupials and monotremes, making them potentially more sensitive to rising temperatures. Birds may be better adapted to survival than larger mammals, as their generally smaller size means they need less oxygen. What's more, migratory birds in particular would be better equipped than animals of a similar size, thanks to their ability to travel long distances in search of cooler refuges. Nevertheless, the number of such refuges would decrease as temperatures continue to rise. These refuges would also be likely to be found at higher altitudes, where less land surface would be available, limiting population size as species migrate to higher altitudes. Ectothermic vertebrates such as fish, amphibians, and reptiles could survive longer than endothermic animals in this scenario, thanks to their better heat tolerance and generally lower oxygen requirements. However, reduced water availability would make some amphibian species more vulnerable in such an environment. Fish species would also be at risk, although rapid evaporation from the oceans would not occur at this stage. Marine species may have a better survival capacity than freshwater species due to the greater volume of ocean water compared with freshwater. For ectotherms, ambient temperature influences their metabolic rate. An increase in ambient temperature would lead to an increase in metabolic rate, and therefore a greater need for food. As a result, surviving species could be exposed to starvation. Reptile species whose sex determination depends on temperatures would be more sensitive to rising temperatures. Invertebrates could be the last animals on Earth before all animal species disappear. Some insects, such as beetles, can survive temperatures of up to 56 degrees Celsius, or 133 degrees Fahrenheit. In general, terrestrial life would initially be more vulnerable than marine life, due to the regulating effects of water temperature. However, the loss of terrestrial vegetation would lead to a reduction in nutrients reaching the oceans. Isolated communities in marine ecosystems, such as animal populations living near volcanic vents, would probably survive longer. Depending on the half-life of oxygen in the atmosphere, animal life could persist for up to 100 million years after the disappearance of plants. Some cyanobacteria and phytoplankton could survive without plants, as they are able to tolerate carbon dioxide levels as low as 1 part per million. They could persist until the atmosphere becomes too depleted of carbon dioxide to allow any form of photosynthesis. In one study, researchers claimed that a specific form of animal life could persist even after most plant life on Earth had disappeared. They used fossil evidence from the Burgess Shale in British Columbia, Canada, to study the climate of the Cambrian explosion, and used it to predict the future climate when global temperatures would rise due to a warming sun and decreasing oxygen levels, leading to the ultimate extinction of animal life. Initially, they expected some insects, lizards, birds, and small mammals to persist, as well as marine life. However, without a continuous supply of oxygen from plant life, they estimated that animals would probably die of asphyxiation. Even if enough oxygen were to remain in the atmosphere, thanks to the persistence of some form of photosynthesis, steadily rising global temperatures would lead to a progressive loss of biodiversity. As temperatures continue to rise, the last animals will be forced to move to the polar regions, or even underground. They would mainly be active during polar night periods, and would go into aestivation during polar day periods due to the intense heat. Much of the Earth's surface would become an arid desert, and life would concentrate mainly in the oceans. However, due to a decrease in the input of organic matter from the land and a reduction in dissolved oxygen, marine life would also disappear, following a similar pattern to that of the land surface. This process would begin with the loss of freshwater species and end with the invertebrates, particularly those not dependent on living plants, such as termites, or those found near hydrothermal springs, such as worms of the Riftia genus. Without CO2, photosynthesis can no longer take place. Without plant life to recycle oxygen back into the atmosphere, free oxygen and the ozone layer will disappear from the atmosphere, allowing intense levels of deadly UV light to reach the surface. As a result of these processes, multicellular life forms could become extinct in around 800 million years, and eukaryotes in 1.3 billion years, leaving only prokaryotes. To meet the Sun's energy needs, the nuclear fusion reactions taking place at its core convert around 500 tons of hydrogen into helium every second. The main effect of this alchemy is a progressive reduction in the number of particles of energy the Sun releases. This is why the Sun's luminosity increases with the passage of time. Thanks to an effective greenhouse effect, the Earth has maintained a stable temperature, apart from a few periods of glaciation, which have enabled life to evolve on its surface. For hundreds of millions of years, the Earth has not undergone any significant change in its ocean mass, thanks to the near equilibrium of mantle water inflows and outflows. To maintain water in a liquid state on our planet, it is essential to establish a balance between the solar energy absorbed and that emitted, enabling us to maintain adequate temperatures. This balance is crucial to the survival of life as we know it. When the amount of greenhouse gases in the Earth's atmosphere increases, as is currently the case, a new energy balance is created, where the greenhouse effect creates an additional blanket, causing the surface to warm up. The Earth has an integrated regulating mechanism called the carbonate-silicate cycle, which controls the amount of carbon dioxide in the atmosphere to maintain a stable climate. Unfortunately, this cycle operates on a timescale of the order of 1 million years, making it too slow to be an effective solution for the current global warming problem we humans face. Progressively, even during the current calm period of hydrogen combustion, the Sun is inexorably rising in temperature. Some 4.5 billion years ago, at the very beginning, its luminosity was equivalent to 70% of today's level. By the time of the Great Oxygen Event some 2.4 billion years ago, its brightness had already reached 85% of today's level. For the next billion years, the Sun will continue to produce nuclear energy by converting hydrogen into helium. This is what almost all stars do most of the time. As the Sun converts hydrogen to helium in its core, the average molecular weight increases, leading to a rise in core temperature and the speed of the fusion reaction, known as the proton-proton chain. This gradually leads to an increase in the star's energy release. As a result, the Sun will shine even brighter. When the amount of incoming energy increases, it can also contribute to global warming. This is precisely what happens when the Sun's brightness gradually increases. Although the Earth's climate may experience shorter-term variations due to the seasons, changes in atmospheric composition, such as the addition of man-made greenhouse gases, as well as factors such as volcanic dust and Milankovitch cycles, the Earth's surface is experiencing a slow but steady warming due to increasing solar luminosity. Over a period of time, perhaps even several 100 million years, the Earth's feedback may attenuate this effect. The greater the thermal energy, the more intense the evaporation, hence the increase in cloud cover, which contributes to the reflection of most sunlight back into space. Increased thermal energy means faster weathering of rocks, greater absorption of carbon dioxide, and lower levels of greenhouse gases. Thus, negative feedbacks will preserve life-supporting conditions on Earth long enough. At some point, the Earth's atmosphere will reach a threshold where it will no longer be able to maintain a stable energy balance, leading to an amplification of the greenhouse effect. This phenomenon is often likened to a runaway greenhouse, characterized by positive feedback. As the planet's surface warms up, water evaporation from the atmosphere increases. Water is a powerful greenhouse gas, which reinforces the greenhouse effect and further warms the planet's surface. For several million years, cellular life can persist in such conditions. However, the critical moment will inevitably arrive when the greenhouse effect becomes uncontrollable, warming the Earth's surface to the point where the oceans reach a state of complete evaporation. Despite the increased amount of water vapor near the Earth's surface, there will be no liquid ocean left. After that, it will only take a few 100 million years for the oceans to evaporate, transforming the atmosphere into an endless pool of steam. When ultraviolet light interacts with atmospheric gas, it can cause the gas to heat up further, meaning that more heat is transferred to atmospheric water when it interacts with extreme ultraviolet light. As a result, the water absorbs more energy and heats up faster. This leads to an increase in water evaporation, and consequently, a more rapid loss of water from the Earth's surface. Another way of explaining this is to use the concept of the habitable zone, which refers to the orbital region around a star where a planet can maintain liquid water, provided it has a suitable atmosphere. At present, the inner edge of the Sun's habitable zone is around 95% of the distance between the Earth and the Sun. Our planet will then be completely devoid of life, but the real apocalypse will come later. As the Sun's luminosity increases, the inner edge of the habitable zone will move progressively further out. It's hard to say exactly when the inner edge of the habitable zone will reach the Earth's orbit, but it's estimated to be around 1 billion years. Some extremophiles may still live in refuges at higher latitudes or deep underground, but these will only be ephemeral remnants of a once exuberant biosphere, a situation that could recall the attractive symmetry of life's beginnings on Earth. In all likelihood, Earth will follow the fate of Venus, becoming a hot, barren world. As the habitable zone of our Sun has shifted towards the outer solar system, Mars is now located in this zone. It is possible that Mars's surface temperature will gradually rise. Carbon dioxide and water currently frozen beneath the Martian soil will be released into the atmosphere, creating a greenhouse effect. This will warm the planet until it reaches conditions comparable to those on Earth today, potentially offering a new island for life. According to computer models, the Moon's presence seems to stabilize the Earth's obliquity, helping to avoid dramatic climate changes. This stability is due to the fact that the Moon accelerates the precessional motion of the Earth's rotational axis, preventing resonances between the precession of the rotation and the precession of the planet's orbital plane. The tidal acceleration caused by the Moon slows the Earth's rotation and increases the distance between the Earth and the Moon. As the semi-major axis of the Moon's orbit continues to increase, this stabilizing effect will diminish. At some point, the disturbances will probably lead to chaotic variations in the Earth's obliquity, and the tilt axis could tilt to angles as high as 90 degrees to the plane of the orbit. This is estimated to happen between 1.5 and 4.5 billion years ago. High obliquity would probably lead to dramatic climate changes and could compromise the planet's habitability. When the Earth's axial tilt exceeds 54 degrees, annual insolation at the equator becomes lower than at the poles. It is possible for the planet to maintain an obliquity of 60 degrees to 90 degrees for periods as long as 10 million years. The likely consequence is that ocean evaporation, plate tectonics, and the entire carbon cycle will come to an end. This could happen in around 2 to 3 billion years' time, when the planet's magnetic dynamo could cease to function, leading to the decomposition of the magnetosphere. This would lead to an accelerated loss of volatile elements from the outer atmosphere. In 2.8 billion years, the Earth's surface temperature, even at the poles, averages 147 degrees Celsius, or 297 degrees Fahrenheit. Life is reduced to single-cell colonies in isolated and scattered microenvironments, such as underground caves, and dies out everywhere else. Every second, the sun emits a solar wind in the direction of our planet, corresponding to a flow of 1 million tons of protons and electrons. These particles are stopped in their tracks by the Van Allen belts, the Earth's magnetic field. Stretching over 70,000 kilometers or 43,000 miles, it originates from the Earth's iron-nickel core. The core is composed of a solid part, the seed, and a liquid layer 2,000 kilometers or 1,240 miles thick. The uninterrupted stirring of the liquid metal layer leads to the formation of the magnetic field. At present, the radius of the inner core is increasing at an average rate of around 0.5 millimeters per year, at the expense of the outer core. Virtually all the energy required to power the dynamo is supplied by the inner core. Within 3 billion years, the inner core is expected to absorb most, if not all, of the outer core, resulting in an almost entirely solidified core, composed mainly of iron and other heavy elements. The remaining liquid envelope will consist mainly of lighter elements that will undergo less mixing. Tectonic plate dynamics are generated by the transfer of heat from the Earth's core to the surface. This heat transfer takes place through the mantle by convection, sometimes combined with thermal conduction. When heat plumes reach the crust, they reach their heat and are pushed out by new hot plumes. This horizontal movement in the upper mantle is the driving force behind the movement of tectonic plates. However, as the Earth cools over time, the liquid outer core gradually solidifies. This solidification reduces convection in the mantle, limiting the power available to move the plates. Eventually, after around 3 billion years, convection will cease completely, putting an end to tectonic plate movements. If plate tectonics cease at some point, the Earth's interior will cool less efficiently, slowing or even halting the growth of the inner core. In both cases, this could lead to the loss of the magnetic dynamo. Without a functional dynamo, the Earth's magnetic field will weaken rapidly over a geologically short period of around 10,000 years. The disappearance of the magnetosphere will lead to increased erosion of light elements, notably hydrogen, from the Earth's atmosphere into space, creating conditions less conducive to life. In around 4 billion years, the increase in temperature at the Earth's surface will trigger an uncontrollable greenhouse effect, creating conditions even more extreme than those on Venus today. This will heat up the atmosphere and raise the surface temperature above 500 degrees Celsius or 932 degrees Fahrenheit, high enough to melt the planet's surface in some places. Nevertheless, much of the atmosphere will be retained until the sun enters its red giant phase. At that point, the Earth's biosignatures will disappear, to be replaced by signatures caused by non-biological processes. From then on, all traces of Earth's life history will be completely erased. In 4.5 billion years, interactions between the Andromeda Galaxy M31 and the Milky Way will form a new galaxy called Milkomeda. The Andromeda Galaxy, also known as M31, is a spiral galaxy containing up to 1,000 billion stars, compared with 300 to 400 billion for the Milky Way. Made up of gas and dust, it adopts a flattened disk shape and contains a bulge at its center. Originally located 2.55 million light-years away, the Andromeda Galaxy has always been the closest to the Milky Way. It has been gradually closing in on the Milky Way at a speed of 120 kilometers per second, or 75 miles per hour. At first, the two galaxies don't seem to have collided. Being so far apart, the stars will initially pass each other without colliding head-on, before moving apart. Sometime later, this apparent choreography leads to a new rapprochement, this time followed by a strong interaction between the two galaxies. Their orbits are strongly affected by the anarchy of gravitational forces in place during the galaxy's interpenetration. The result, after 2 billion years, is the birth of a gigantic system with little interstellar gas, a new galaxy, Milkomeda. Unlike its two parents, this new galaxy is elliptical in shape, and the stars it contains are scattered around a sphere. The Milky Way and M31 no longer exist. This collision will not disrupt the orbits of planets within the solar system. While the gravity of passing stars can detach planets in interstellar space, the distances between stars are so great that the probability of the Milky Way-Andromeda collision causing disruption to a given star system is negligible. Although the solar system as a whole could be affected by these events, the Sun and planets are unlikely to be disturbed. The new galaxy sees a new outburst of stars, but as the little remaining gas is rapidly consumed, star formation comes to a halt, and the new galaxy will slowly fade away as its new stars die out. In 5 billion years' time, the Sun will leave its main sequence and begin its transformation into a red giant, having exhausted the hydrogen reserves in its core. The energy released during the fusion of hydrogen nuclei in the Sun's core fuels the frenetic agitation of lively particles that exert a powerful outward pressure. It is thanks to this pressure that the Sun swells and does not collapse under its own weight. Until now, this balance has been maintained, but now at 5 billion years, this is no longer the case. Although the Sun still abounds in hydrogen nuclei, there are virtually none left in its core. Hydrogen fusion produces helium, whose nuclei are heavier and denser than those of hydrogen. It is in the core of the Sun that the temperature is highest, at around 15 million degrees Celsius, or 27 million degrees Fahrenheit. The fusion of hydrogen into helium requires 10 million degrees Celsius, or 18 million degrees Fahrenheit. On the other hand, helium fusion requires a temperature of the order of 100 million degrees Celsius, or 180 million degrees Fahrenheit. The Sun is nowhere near this threshold, so as helium replaces hydrogen in the core, the fuel supply for fusion will diminish. Pressure from energy production will decline, and gravity will prevail, causing the Sun to implode. As its gigantic mass collapses in on itself, the Sun's temperature will rise dramatically. Despite this pressure and extreme temperature, helium fusion is still not possible, and the hydrogen then triggers a second phase of fusion within a thin layer around the helium core. As hydrogen fusion proceeds at an inordinate rate, the thrust is much more intense than before. The Sun swells to colossal proportions, reaching over 100 million kilometers, or 62 million miles in diameter, almost 100 times its current diameter. Transforming into a pulsating red giant, it will become thousands of times brighter than it is today. It leaves its main sequence to become a red giant. Naturally, the planets in the solar system will be directly affected by this change. The Sun, with its diminished mass, exerts less gravitational attraction, enabling the planets to migrate to more distant orbits. But do the planets go far enough to win the race against the Sun's increasing diameter? Mercury loses the race, swallowed by the Sun and briefly vaporized. Mars, orbiting further out, escapes unscathed. Venus is lucky. The Sun stops swelling just before it reaches its new orbit, and at the same time, the Earth is also spared. Nevertheless, conditions are fundamentally different. Earth and Mars rotate synchronously with the Sun. The average temperature is now several thousand degrees. What does a sunrise look like from Earth today? Instead of a warm, cheerful yellow disk, a gigantic red circle slowly settles above the horizon. It won't be long before Mars suffers the same fate as Earth. The atmosphere begins to warm. Potential life forms on this planet won't survive another 1 billion years. 2 new orbits are now taking their place in our solar system's habitable zone, the orbits of Jupiter and Saturn. Although neither planet is conducive to life, either Jupiter with water in its clouds or Saturn, made up entirely of gas, their respective moons could become suitable places for the appearance of primitive life once their temperatures have risen. In this way, simple organisms could see life on the surface of Saturn's moons, Enceladus or Titan, or Jupiter's moon, Europa. Most of the Earth's atmosphere will gradually be lost to space. The Earth's surface will be transformed into an ocean of lava, with floating continents of metals and metal oxides and icebergs of refractory materials. Surface temperatures will rise dramatically, exceeding 2,000 degrees Celsius or 3,632 degrees Fahrenheit. Then, over 12 billion years old, the Sun's most rapid expansion phase as a red giant will occur in its final stages in 7.4 billion years' time. At this stage, it is likely to expand sufficiently to reach a maximum radius of around 1.2 astronomical units. The Sun will have lost more than a third of its current mass, which will have dispersed in the form of an intense solar wind. This loss of mass will cause the orbits of each planet to expand considerably. Considering only this phenomenon, Venus and Earth could probably escape incineration, but other studies suggest that the 2 planets would still be absorbed due to tidal interactions with the tenuous gas of the Sun's expanded outer envelope. Forecasts for the end of our planet are therefore rather gloomy. The Earth's gravitational interaction with the Sun's outer atmosphere will cause the Earth's orbit to shrink. The drag effect of the Sun's chromosphere will progressively reduce the Earth's orbit. These effects will partly compensate for the Sun's loss of mass, making it likely that the Sun will eventually engulf the Earth in around 7.59 billion years. The Sun's atmospheric drag can also cause the Moon's orbit to disintegrate. As the Moon's orbit approaches a distance of 18,470 kilometers, or 11,477 miles, it will cross the Earth's Roche limit, meaning that tidal forces exerted by the Earth will break the Moon apart, transforming it into a system of rings. Most of these orbital rings will begin to decay, and the residual debris will impact the Earth. As a result, even if the Sun doesn't directly engulf the Earth, it's possible that the planet will be left without a moon. But the Earth's decaying trajectory towards the Sun may eliminate the Earth's mantle, leaving only its core. Eventually, the Earth's core would also be destroyed 200 years later. According to this gloomy scenario, the Sun's red giant will simply destroy the Earth, which will evaporate into the hot solar atmosphere and cease to exist. But the story of the Sun as a red giant doesn't end there. As the hydrogen nuclei continue to fuse around the core, more helium will flow into the center, and the temperature will rise even higher. The cycle is fueled. Hydrogen fusion in the shell around the core accelerates, and the helium deluge at the center intensifies. This phase will last 500 million years before the core finally reaches the temperature required for helium fusion, a process that produces carbon and oxygen. This transition from hydrogen to helium fusion is marked by a spectacular eruption, during which the Sun contracts to a more constant subgiant structure. This new equilibrium was short-lived. 100 million years later, in the same way that helium had displaced hydrogen, carbon and oxygen nuclei drove helium out of the core and into neighboring layers. The combustion of oxygen and carbon now requires higher temperatures, at least 600 million degrees Celsius. This time, the core will never reach the temperature required to restart nuclear reactions. Its mass is not high enough to reach the temperatures required to fuse carbon and hydrogen nuclei into heavier, more complex elements. The helium shell continues to burn, and the core continues to contract until Pauli's exclusion principle stops the implosion. This quantum mechanism acts as a repulsion. It's as if the electrons refuse to be compressed any further, bringing the Sun's contraction to an end. The outer layers continue to expand and cool before being scattered across the cosmos. All that remains is a staggeringly dense ball of carbon and oxygen, known as a white dwarf. It will continue to glow for another few billion years. Fusion reactions will cease, and the temperature is no longer high enough. The Sun's thermal energy will be gently dissipated into space, leaving a dark, cold globe. In 9 billion years, the Sun, with a mass equal to 54% of its current mass, will become a white dwarf, composed of carbon and oxygen. Our Sun is now dead, and its core laid bare. Its power of attraction on orbiting bodies such as planets, comets, and asteroids will have weakened due to its loss of mass in the previous stages. All the orbits of the remaining planets will expand. If the Earth is still around, its orbit is now twice as far away as the orbit we know today. All the planets will become dark, icy, and completely devoid of any form of life. They will continue to orbit their star, their speed reduced by the increased distance from the Sun and its reduced gravity. More than 4 billion years later, the white dwarf Sun has cooled to a temperature of 2,000 degrees Celsius, or 3,632 degrees Fahrenheit. Its luminosity falls below that of the Sun. Its luminosity falls below 3 billionths of its current level. Its heat is no longer measurable. It is now invisible to the human eye. So weak is its radiation that it is drowned in that of the cosmic microwave background. The Sun is gradually changing from a white dwarf to a black dwarf. The prospects for the destruction of our planet are not merely speculative, but based on solid predictions based on our scientific advances. Although we have knowledge of the Earth's distant future, it is up to us to shape the short-term future. This perspective raises fundamental questions about the future of life on Earth, and our responsibility as a species to be aware of this potential future. It is crucial that we deepen our scientific knowledge, develop environmental preservation strategies, and explore innovative solutions to prepare our planet's biodiversity and sustainability. While this may seem a long way off on a human scale, it remains an inescapable reality in the natural evolution of our solar system. Understanding these phenomena and their implications enables us to better appreciate the importance of preserving our environment and exploring new avenues to ensure a sustainable future for generations to come. This is the ultimate dream of a scientifically literate society, and our only hope of staving off, as far as possible, the imminent threat of human extinction.